Hi, I'm John Doherty. I'm the author of PEST. I've also been a significant contributor to GMDSI training and worked examples over the last few years. So this video is in two parts. The first part is rather philosophical in nature. The second part demonstrates how that philosophy can be applied with some real-world problems. I think that it is time to talk a little bit about philosophy. I believe that groundwater modelling has enormous potential to help us manage hugely complex groundwater systems. I also think it's not quite living up to that potential. Our job is to bring science to bear in management of groundwater systems, and to do that we need to understand a little bit about just how science can be applied, and any exact science can be applied to the management of these complex systems. So there's a lot of training material, there's a lot of advice that we're given, there's a lot of guidance documents, textbooks, and they throw at us a number of concepts, some of which are illustrated on this slide. And in my opinion, there's a lot of confusion as to how these concepts should be put together into a coherent whole that allows us to apply science to the management of complex systems that we don't know too much about. So let's spend a little bit of time examining how we can do this, how we can fit the pieces together, the philosophy that we should use in fitting the pieces together when we try to help people manage a groundwater system and bring science to bear on the management of that system. So, if we're going to talk about science, if we're going to talk about philosophy, let's spend a little bit of time talking about the scientific method itself. Now, I certainly am not an expert on scientific philosophy. I would like to draw your attention, however, to something that I read recently, written by Jeff Kars, a petroleum engineer from Stanford University. I did draw a lot of inspiration from this article and I refer you to it. Jeff sees Bayesianism as the best way to implement the scientific method in the field of petroleum reservoir modelling. I think that makes sense. However, I think that groundwater modelling is a little bit different, and perhaps the conclusions that we draw on how to apply the scientific method to groundwater modelling may end up being a little bit different. But just a few moments on what is the scientific method. At the heart of the scientific method is logic, and what is logic? There are two approaches to the scientific method here. They're not mutually exclusive, but they're based on different ideas of logic, the different types of logic that can be brought to bear in operating, in using the scientific method at a particular site. Inductive logic. The inductive logic goes something like this, that the sun rose yesterday, the sun rose this morning, it's pretty likely that it'll rise again tomorrow. So we can see the regularities here, we turn them into principles, we make calculations on the basis of those principles and we apply them. And some say that perhaps the purest form of application of inductive logic are Bayesian methods. We'll talk about Bayesian methods shortly. There's another approach to exposés on the scientific method, and I'm sure you've all heard of Karl Popper and the notion of falsification. The idea here is that when it comes to science, knowledge is kind of asymmetric, and it applies particularly to what happens under the ground, I suppose. We can't know what's under the ground, but we can know what's not under the ground. We can propose a hypothesis. You can never accept a hypothesis, you can only reject a hypothesis, and you can reject it only if it's demonstrably incompatible with measurements that you make of a system or something that we already know for certain. Some say that the best implementation of this approach to scientific thinking is frequentist statistical methods. So, as I said, we don't have to choose between these, but we can draw inspiration from both of them, and perhaps as we attempt to apply the scientific method in groundwater modelling, we can ask which method or which way of thinking takes us the most distance in solving the different management problems that we're presented with every day. So before examining this, I just want to spend a few moments showing you a synthetic example, just to show you the sort of field that we're operating in, just to show you the inexact nature of the science that we have to apply. Now, the inexactness of this science actually probably makes adoption of the correct philosophy all the more important, because its inexact nature is going to require of us that subjective judgments be made, as well as complicated processing of complicated data to draw complicated conclusions, still implementing the scientific method the best we can. So these slides, actually, any of you who have heard my talks in the past, some will maybe have already seen these slides. I apologise if that's the case. These were done by a PhD student that I had 20 years ago. However, the conclusions are just as relevant now as they were then. So we have a model domain, a synthetic model. We have water flowing in from the top of the system, and it flows to the bottom of the system. We release a particle near the top of the model domain, and it winds its weary way to the bottom of the model domain through a heterogeneous hydraulic conductivity field. This is how long it takes to reach the bottom of the system, 3, 2, 5, 6 days. Now I'm going to pretend that I do not know the hydraulic conductivity of the medium. Instead, I'm just going to use this model to generate 12 heads, and I'm going to calibrate another model against the 12 heads and make the prediction using that calibrated model. There's no noise associated with this data, therefore I can fit it perfectly. And I do, and when I do, here's the hydraulic conductivity field that I obtain. Now you can see it's not reality. Well, it was never going to be reality. There's only 12 pieces of information in my calibration data set. All that I can produce is a kind of reflection, a pale reflection, a low resolution image of reality. And when I do, I can make a prediction with my perfectly calibrated model, and I get an answer that's perfectly wrong. So what conclusions can I draw from this? Well, there's a number of conclusions we can draw from this. Firstly, history matching is non-unique. There are many different ways to fit 12 head measurements. So certainty is something that when it comes to groundwater modelling, I will never have. The second thing is, just because something calls itself the calibrated model, this doesn't mean that it has the license or the power to give the right answer. In fact, giving the right answer is not something we should expect from a groundwater model. There's no mathematical reason why we should expect the right answer. It is not the metric by which a good groundwater model should be judged. The calibrated model, in calibrating a model, we seek a unique parameter field. Uniqueness comes at a cost. It's not real, it's just that it's a parameter field that fits the data and has the potential to give predictions that are somewhere near the center of the posterior probability distribution of those predictions. When I quantify the uncertainty of this particular prediction, I do find that the right answer is within the uncertainty interval of the quantified uncertainty limits. And that's the metric that we should be using for judging a groundwater model. Not that the model gives the right answer. We should accept that no model is necessarily going to give the right answer, because there could be an awful lot of potential for wrongness in any answer that a history-matched model gives. What I have to do is guarantee that when I quantify the uncertainty of a decision-critical prediction, the right answer lies within the uncertainty limits. And in this case, it does. So the good model is that which quantifies uncertainty of decision-critical predictions and reduces that uncertainty as much as the data set allows. And that's what determines the final margin of uncertainty. How much data we have, not the fact that we can fit the data we have perfectly. So now, let me spend a little while inquiring into how we do groundwater modelling at the moment. Now, I think these days we recognise that we can't ignore uncertainty. And I think that even though there's a huge variation between how well groundwater modelling is done, ranges from very poorly to quite well, I think implicitly or explicitly, most modelling these days attempts to apply something approaching the Bayesian philosophy. And to understand that, we just need to understand Bayes' equation, and I'm sure most of you are familiar with Bayes' equation. Bayes' equation says that we start off with a prior probability distribution. And this accepts the fact that our knowledge is incomplete, that especially hydrogeological knowledge needs to be expressed stochastically. We know maybe something about the geology at our site. We may have spent a lot of money in site characterization. This gives us dots that we can join probabilistically to come up with an idea of what's under the surface. Now, our knowledge is far from exact, so as I said, it has to be expressed stochastically. This means that notionally we can come up with all different figments of our imagination based on geological principles and constrained by measurements we've made at the site. And we can come up with all different pictures of what may be under the ground. Now, not any figment of our imagination that we can conjure up can be used in a model, because we can conjure up a set of properties and structures that exist under the ground, put them into a model, run the model, and the model doesn't reproduce the present or historical behaviour of the system. Well, therefore, it can't be correct. Now, nothing we conjure up is going to be correct. However, if it can't reproduce the historical behaviour of the system, it won't be able to reproduce the future behaviour of the system, which is why we're building the model. So we have a basis for rejection of certain figments of our imagination. If we're going to use those in a model, they have to be able to allow that model to reproduce the past behaviour of the system. This term here is called the likelihood function. It rises in accordance with the model's ability to replicate measurements of state and flux. So we combine these two terms together, conjuring up figments of imagination according to a prior probability distribution, filtering those according to the necessity to reproduce the behaviour of the system. And by doing that, and it's a complex thing to do, it's easy to write in this simple equation, it's very difficult to do numerically, but if we do, we come up with a posterior probability distribution of parameters. If we then run our model using samples of this posterior distribution of parameters, run it enough times, we can sample the posterior probability distribution of predictions that we care about. And that way, we've given the decision support process what it needs, a probability distribution of a prediction of management interest, constrained by the necessity that we've got to be able to replicate how the system works as embodied in measurements of its state and fluxes. So, how do we do this in practice? Well, the guidance documents normally give us a number of clear steps, and we'll just go through those steps now. We can ask, do all of them make sense, or what is required of these steps in order that the precepts, the potential of this Bayesian approach is realised? The first step, we're told, is to build the conceptual model. Now, the conceptual model is the hydrogeologist's playground. He or she can come up with all the details of what may exist under the subsurface that can affect the movement, the fate of groundwater and contaminants entrained therein. And often a lot of investment is placed into development of this conceptual model, and it's with some pride that a hydrogeologist may then come up with a fairly detailed conceptual model and then say to the modeler, can you please make sure that this numerical model encapsulates all this detail that I've just gone to so much trouble to give you. So this model then is built under the precept that it needs to look like the real thing as encapsulated in this hydrogeological conceptual model. But this is where things can start to go wrong. If details matter, then do we know the details of the detail? Probably not. Now there's a paradox there, and a paradox that's never going to go away and we have to overcome. If we don't know the details of the detail, those details have to be expressed stochastically. And they have to be expressed stochastically not just here, but here, in the complex model. But often the complex model is given a complex structure, not so that it can express stochastic details, but so that it can express one realization of the details here, because it has to look realistic. Why? Well, this is something we'll talk about, but looking realistic and implementing the scientific method become two different things when this cannot express the stochasticity of this. But let's move on. So the complex model is built that looks like the real thing, and often it is then given a fairly simplistic parameter field. Why do we give a simplistic parameter field to a structurally complex model? Well, often at this stage we're getting a little bit overwhelmed with the complexity of this monster we're creating. And we don't recognize the fact that if structure is complex, well, each one of the units that we define has complex sets of hydraulic properties, which implies complex and stochastic parameterization. However, that's often forgotten. We often use simple parameterization scheme and try to make it stochastic, but because it's simple, there are very definite upper limits to the stochasticity that a simplified zone-based, for example, parameter field can express. So then we try to history match, we try to calibrate this model. And often we don't get a very good fit with the data. This structure might not be right. It's one realization of a stochastic conceptual model after all. The parameter field is simplistic. We don't fit the nuances of the data. But then we make excuses for ourselves. We say, if I fit the data too well, it would be overfitting. And we say, here's a RMS figure that I've got out of some guidance documents, 5% normalized RMS. That's a good enough fit. The guidance documents tell me so. And so I'm ignoring often important nuances of a system that may be rich in information, but I shut the door saying, it'd be overfitting if I fit that. And the real reason is because I can't fit it. And if there's any surprises in this data, they're ignored. There's no place for them in this rigid conceptual model. But anyway, I build a model, I calibrate it, and then I do sensitivity analysis. Now, what is sensitivity analysis? As you'd probably know, there's lots of nice, insightful things we can do with linear analysis as encapsulated in programs of the PEST and PEST++ suites. But traditional sensitivity analysis applied to groundwater modelling, it's often a hangover from the days where we were told that parameter parsimony needed to prevail and sensitivity analysis could tell you whether you're using too many or too few parameters. These days, when I see it done, it often has little meaning. It's done just because we're told to do it. There's no carefully defined insights that we're trying to obtain through clever linear analysis. But anyway, we do sensitivity analysis because it's there in the guidance documents. And then if we're lucky, we do nonlinear uncertainty analysis, where we attempt to quantify the uncertainties of decision-critical predictions. However, this has become difficult. We've got often a parsimonious parameterization scheme. When we do uncertainty analysis, when we quantify predictive uncertainty, can we be sure that the right answer is within the uncertainty limits? Often not. So this sort of summarizes those steps. Conceptual model, numerical model, tries to look like the real thing, and here at some late stage comes in the data, and then we quantify uncertainty. Does this work? Well, I would say no, but before I say no, we've got to define what work means. Well, basically work is the opposite of not working, and not working is failure. Now, I've written on this subject, and I think decision support modeling gives us a very clear definition of failure. Let's define it, and then let's ask whether modeling as traditionally done, as I've just outlined, actually works. So what is failure, first of all? Well, normally when we're building a model, we're building a model to help someone manage a system. And what does system management mean? System management means that we're attempting to ensure that some bad thing doesn't happen. Normally it's the bad things that define the management context, the bad things we don't want to happen. As we'll talk about later, we can actually use these bad things as hypotheses and see whether we can reject them. This gives us an ability to define failure. If we do our model, and if we say that if you do this, if you manage the system in this way, this bad thing won't happen, and if that bad thing can actually happen, but we've ruled out the possibility through insufficiently wide uncertainty limits on our predictions, then we have failed. That's a type 2 statistical error. If we say this won't happen, and it actually can, we have done a disservice to the management process. This is decision support modeling failure. So, having defined failure and hence lack of failure, does this work? We can now ask, does this work? Well, firstly, as we said before, if this whole process is going to be scientific, and hopefully it's application of science that allows it to work, this conceptual model needs to be stochastic. In recognition of the fact that details are important, but the details of the details are unknown, and providing stochastic expression for geological details is a very difficult thing to do. And if this is stochastic, this has got to be stochastic. Now, here we've got a complex numerical encapsulation of a figment of imagination with a complex structure, possibly many layers and a lot of things like faults and structure hardwired in. But the more detail we've hardwired into the structure of this model, the more it becomes one realization of the many that need to express the uncertainty of the situation we're dealing with. Structure cannot express stochasticity, parameters can. And a structurally complex and often parametrically simple model is doing the very opposite of what is required when we've got a stochastic conceptual model. This has to be able to express the stochasticity that this should express. Complex structure does not express stochasticity. It hardwires in one realization of stochasticity which is probably wrong. Therefore, predictions may actually be biased because of the complexity of this model. And then when we try to do our history matching, this monstrosity takes a long time to run. It's probably numerically unstable. Very difficult to use with software like PEST and PEST++. We don't get a very good fit with the data, but as I said before, we actually try to turn that into a blessing rather than a curse. We actually say, oh, that's a good thing, when we should be asking, why am I not fitting important nuances of system behavior which might be telling me a lot about what can happen in the future when I manage this system? And what if my conceptual model's not quite right? What if these nuances of behavior are telling me things I didn't know? Where is the capacity to learn? Where is the ability to accommodate surprises in this whole structure that we've set up? This structure, this way of doing things, this traditional workflow actually gags data. It does not allow it to be heard. And because of that, it is not scientific. We cannot say that this is an encapsulation, an embodiment of the scientific method as applied to groundwater management. Why do we do it? Well, tradition. We do it because we're scared someone will criticize us if our numerical model doesn't look like whatever figment of their imagination they believe to be the real thing. Our job is to process groundwater data. It is not to give numerical voice to figments of someone's imagination. Certainly, hydrogeological wisdom has to be an important part of modelling, but that hydrogeological wisdom, that part of science that has to be expressed in our scientific workflow, has to be expressed in ways that are different from this workflow. This workflow is not the implementation of the scientific method. So let's ask ourselves whether there's a better way to implement the scientific method when we're helping people to make decisions about groundwater management, when we're trying to bring science to bear in the decision-making process. So let's go back to the two approaches to the scientific method that we talked about before. And now let's focus on this approach. Now again, this is a continuum. That does not mean that we exclude the Bayesian approach. We're asking here if, given the nuances of our inexact science and what we can contribute to decision making through implementation of the scientific method, is there perhaps some inspiration to be gained through examining the precepts of the Popperian approach? So that means, as you're all familiar with, I'm sure, we need to propose a hypothesis. That's the way it goes, and we see whether we can reject that hypothesis. You can't accept a hypothesis. There could be many hypotheses that remain unrejected, but you can only reject a hypothesis, and then you can only reject it if it is demonstrably incompatible with the behavior of the system. So ideally, the scientist sets up an experiment, takes some measurements, and if those measurements say that your current thinking on what's happening here is contradicted by these measurements, that hypothesis is rejected. Now we can apply the same idea to groundwater modelling and the scientific assistance that we provide to the management process. So if we're going to do this, the first question we ask, which hypotheses are we testing here? If we look at the traditional workflow, which I've just been talking about, one of the problems there is that there's so many hypotheses encapsulated in the complex conceptual model and then hardwired into the complex numerical model, and then conceptually at least, if this is the model that we're building as our scientific instrument, if this is the means that we're using to process data, there are just too many hypotheses embodied in this process for us to address, for us to test, to know whether we can reject them or not. So we're running into conceptual problems already. What if we limit the hypotheses that we test to just one? And often in a groundwater management context, that hypothesis is presented to us on a silver platter. It is the bad thing that we talked about before. For example, if I'm going to use a resource here, I might ask, what is the impact here? Well, there's the hypothesis. It might be decreed that if I pump water here, the drawdown at this place should not fall below a certain level. That's the bad thing that I don't want to happen. That's the hypothesis that I want to test. That's the hypothesis that I want to see whether I can reject if management is undertaken in a certain way, or if it can't be rejected, demonstrate to decision makers that it can't be rejected. Now, management may entail many hypotheses. There might be a number of criteria that determine what is good management. Perhaps we need different models built to address those different hypotheses. But the point here is that now what we are doing is building a model as a scientific instrument designed to process data that contains the information which may or may not allow me to reject a specific hypothesis, that hypothesis being fundamental to the management of that system. And that hypothesis, or a small number of hypotheses, will often be very apparent in the definition of what is good management of the system. Now, the nice thing about that is that it reduces the complexity and the tractability of the problem enormously. I'm moving a little bit away from the Bayesian idea of having to quantify the posterior uncertainty of a prediction. I'm saying I don't care too much about this part of the posterior probability distribution. What I care about is this part. There's a hypothesis here that I want to test. This is of secondary importance to me. It's only this pessimistic end of the posterior predictive probability distribution that I'm worried about. So, what are the advantages of doing things this way, of thinking about it this way? Well, I think there are a number of advantages. Firstly, I've taken an infinitely complex problem, I've made it one-dimensional. There is only one hypothesis here that I need to test. Excuse me. And when I'm designing my model as a scientific instrument that processes data that is pertinent to that hypothesis, all design decisions can be referred to what this model is trying to do, to the hypothesis that I'm testing. So I have a reference point for every design decision of this model. And as we'll talk about in a moment, the model will must probably be structurally simple, parametrically complex. But that's going to involve compromises. But I have a reference point for any compromise I make in building this scientific instrument to test this specific hypothesis. The model that I build will run fast. It'll be sleek. It can be used in conjunction with software like PEST and PEST++ that can extract data and deliver information to where it's needed. Another nice thing about this is that my criteria for failure is built right into the goal of modeling. When I build this model to assist someone to make a decision, I have to be able to demonstrate to stakeholders that I haven't failed. Well, the criteria is built right into the design of the model. Here's the hypothesis that I have to test. False rejection of that hypothesis is failure. I then have a reference point for assuring stakeholders that I haven't failed. I haven't got to assure them that I'm replicating the subsurface as I do in the traditional approach, because I am most assuredly not replicating the subsurface, because no one can simulate what happens under the ground. But we can process data and we can extract information that can be informative of the repercussions of what happens under the ground to important decisions that we have to make. But most importantly, that complex process of building a simulator becomes cognitively and mathematically more tractable. Yes, I am simulating, but not for the sake of simulating. I am simulating in order to process data and deliver information to where it's needed for a very specific purpose, and that is to test a very specific hypothesis. So, if we're going to picture this new way, or this new workflow, this alternative workflow, still based on the scientific method, what's a good way to picture it? And I refer you at this stage to a document that you can download from the GMDSI website, which talks a lot about appropriate model complexity. So I like to look at this, what we're doing in decision support modeling, as enabling the flow of information, building a transmission line for information. And I think there's metaphors here that can guide us into designing a workflow that actually works in the decision support context. So the first thing I do is I have to get information from data. I have to encode it. So in a model, what carries information? Parameters. Structure is a kind of, it's a structure for housing the things that do the work, and the work is done by the parameters. These convey information. These also express the repercussions of lack of information. Parameters can wiggle. Structure cannot. Parameters can respond to information. They can express lack of information. Structure can do neither of these. To get information from data to parameters, we history match. So we take our structurally simple, parametrically complex model, we use it in conjunction with PEST and PEST++, we encode this information in the model's parameters. So our model becomes a kind of transmission line where information is transmitted from where it resides in data to the decision point where it has to be used. And here it has to be decoded. There's a hypothesis here that we're testing. Now, we're never going to be able to say I can 100% reject a hypothesis. Our ability to simulate what happens under the ground is limited. Our ability to attach prior probability distributions to hydraulic properties is limited. That's one of the problems of working in a Bayesian framework or trying to apply a Bayesian framework to our inexact science. We can't quantify the prior probability distributions in the conceptual model, and even if we could, expressing them numerically in the complementary numerical model is almost impossible. So this decoding at the end is going to have a subjective element. A decision maker has to make a decision on the basis of inputs provided by us. It may be demonstrated that a hypothesis subjectively can be rejected. If I do this, a bad thing won't happen. Or it may be demonstrated that the hypothesis cannot be rejected, but can be assigned a pretty low level of confidence that it'll happen. In the end, a decision has to be made, and in the end, it's going to have to account for the information that we have conveyed to the decision maker, and that information will have to be interpreted subjectively. That's all part of the process. Our job is to get the information from where it resides to where the decision maker can exercise his or her subjectivity in the most constructive way, where they can understand the information from here that's been delivered to him or her in a way that allows him or her to make that decision. And our job as modelers is to build that transmission line. And, as I've already said a number of times now, the principles that allow extraction and delivery of that information is going to rest on the fact that this can be done best with a model that's structurally simple, parametrically complex. Yes, there'll be distortion, there'll be loss of information on this transmission line. There always will be. And structural simplicity may induce its own distortions. There'll be subjectivity in what is an appropriate level of structural simplicity here. But this can't be helped. The thing that I'm saying here is that when we make these subjective decisions on how to encode data, how to decode it, it's all done with a workflow in mind that implements as much as possible the precepts of the scientific method. If we do things a traditional way, we run into so many problems. Implicit in the traditional way of doing things is the idea that no decoding is necessary here. Implicit in the fact that we can build a simulator of what happens under the ground, and that it's somehow or other an accurate simulator of what happens under the ground, is that no subjective decoding is necessary here. Just look at the outputs of the simulator and all you need to know. We've captured what happens under the ground. Well, that to me is ridiculous, yet it is a concept on which so much modelling rests. We can't simulate what happens under the ground, but we can extract and deliver information to where it is needed. A structurally complex, parametrically simple model blocks information rather than delivers it. If we are going to implement the scientific method, we have to deliver information to where hypotheses can be subjectively tested and decisions can be made on the basis of that subjective hypothesis assessment activity that is integral to the making of decisions in complex groundwater systems about which we know so little. So before we finish this first half of the video, I want to say a few words about direct predictive hypothesis testing. So I've mentioned this as a concept of the implementation of the scientific method, but we can, with a numerical groundwater model, actually implement this hypothesis testing procedure quite formally. It'll still be subjective, but it'll be a formal implementation of hypothesis testing. So, suppose that we we've built our model and now we calibrate our model. Now remember I said at the beginning of this video that calibration is a special way of solving a non-unique inverse problem. There's a million ways to fit field data, but when we calibrate we seek a solution to that inverse problem which is of minimized error variance, so the mathematicians call it. We seek out of all the possible ways to fit the calibration data set, we seek a way that gives us the smoothest parameter field, and not on the basis that the world is simple under the ground, but on the basis that when we make predictions, these are the predictions that have minimum potential for wrongness. Because the wrongness is symmetrical with respect to these predictions, they'll be somewhere near the center of the posterior probability distribution. So we calibrate our model, our structurally simple, parametrically complex model, and we normally get a good fit with the data and we get a parameter field that may or may not be complex depending on the data. Now, we're using lots of parameters. We've allowed surprises to occur where they need to. We are responsive to the data. However, because the model is structurally simple, perhaps the parameters are taking on roles that compensate a little bit for the structural simplicity of the model. Perhaps the model is too structurally simple. Well, we've learnt that through the calibration process. We've asked for the smoothest parameter field. If it's obviously too rough, reflective not of hydraulic properties under the ground, but of failure to have certain elements of structure, then we can go back and make that structure a bit more complex. However, we may decide that, well, I don't mind if some of the parameters adopt somewhat surrogate roles for structural defects because it may be biasing the prediction a little bit or not at all. But if I can reduce uncertainties a lot and incur a little bit of bias in the process, then perhaps the ledger is in the black in terms of quantification and reduction of uncertainty. These are decisions that only the modeler can make, and they are subjective decisions. So anyway, my task here is to process data, and as we talked about before, deliver it to where it's needed, and here is my transmission line. Through calibrating this model, I've learned a couple of things. I've fit the data hopefully fairly well. I've got information from that data that could not have been obtained in any other way. I won't get a perfect fit, but I've learnt the fit that I will tolerate. Good enough, hopefully, to get the information which I need. Not so good that I'm biasing important parameters and possibly important predictions. These are subjective judgments. This history matching process done with a structurally simple, parametrically complex model has given me the ability to do this, and there may be some trial and error, but we know what we're trying to do. So I learn, will I accept this fit with the data? Maybe. Okay, here's the parameter field. Maybe I've learned some things about what's happening under the ground that I wouldn't have known if I hadn't had lots of parameters. Maybe there's a few bumps and lumps in this parameter field which indicate the parameters are compensating slightly for structural inadequacies, but I decide to accept it anyway. So, through calibrating this model and seeking the smoothest or minimum error variance solution to the inverse problem, I've learned stuff. I've learned some of the terms actually on the right of Bayes' equation. I've learned about the prior, and that's kind of a paradox that I'm learning about my prior through history matching, and that's possibly why the Bayesian approach in its purest form isn't quite the right thing to do in decision support groundwater modelling, though we can certainly draw a lot of inspiration from that approach, of course. Anyway, I've learnt my prior, I've learnt my likelihood function. In other words, I've learnt what I will tolerate in misfit with the data. I've learnt what I will tolerate in terms of bumps and lumps in this parameter field. Okay, now we go to the future. I've still got my historical data set. I'm still calibrating the model, but now I'm recalibrating it. And I am including in my observation data set, in the calibration data set, one extra observation. I am observing that the thing that I don't want to happen in the future when I manage the system under a proposed management regime, I am observing that that bad thing actually happens. And I'm saying to PEST, make it happen. But I'm using numerical regularization, that's all described in PEST documentation. I'm saying, make this bad thing happen in a way that still gives me as good a fit with the data as you can. So there's the past in there in the revised calibration process, and give me a parameter field that departs from this parameter field only to the minimum extent necessary to fit this hypothesized prediction. And then I look what I've got. Now, if the misfit is too great according to the metric which I had previously accepted when I calibrated, and or if the bumps and lumps in this parameter field are just too great in terms of the metrics for this parameter field which I learnt when I did my previous calibration, if either of those things occur, then I can reject the hypothesis that the bad thing will happen. I can do that because I've demonstrated incompatibility of that hypothesis with the observed behavior of the system and or with the hydraulic properties of the system as they make sense for this particular site. The rejection process it'll be subjective, yes, but I am very directly using groundwater modeling as a scientific instrument directed at a management-specific hypothesis. And its modeling and its data assimilation all rolled into one using PEST or PEST++, dancing with the model to implement the scientific method applied to and supporting the decision-making process. So that brings us to the end of part 1 of this two-part video. Then, as I said previously, the second part of this video will look at a couple of examples of implementing this modeling philosophy at real-world sites.